Now we can consider the second case. What is the electric field intensity on the surface of the shell? See, for that we need to consider the point P on the surface of the shell like this. So what is the distance of point P from the center of the shell? It is capital R. So at the surface of the shell, small r will become, that means small r equals or becomes equal to the radius of the shell, right? Because the distance between the point that we are considering to construct a Gaussian surface is small r, and in this case small r is equal to the radius of the shell, capital R itself. So we know the expression for electric field intensity outside the shell. What is that? E out is equal to sigma r capital R square by epsilon naught into small r square. So if you want to find out electric field intensity on the surface of the shell, just substitute small r equal to capital R in this expression. Okay, so what you will get? You will get E on the surface is equal to sigma into, here small r square is, or capital R square will be equal to small r square, epsilon naught into small r square. Okay, we have just substituted small r equal to capital R in this expression. That is the only modification required to find out electric field intensity on the surface of the shell. So here r square cancel. So what is the expression for electric field intensity on the surface? Sigma by epsilon naught. And from this expression it is very clear. On the surface, electric field intensity is constant. Why? Because sigma is a constant, epsilon naught is a constant. There is no any term involving small r or capital R. So electric field intensity on the surface of the shell is constant. Next, let's discuss the electric field intensity inside the shell. So to find out electric field intensity inside the shell, we need to consider a point P inside the shell at a distance small r from the center. And to apply Gauss's law, we need to construct a Gaussian surface inside the shell. Next, we can apply the Gauss's law, integral E dot Q by epsilon naught, or integral E dot dA is equal to Q by epsilon naught. And when you expand it, you will get E into dA, because electric field and area element vector are acting along the same direction, equal to Q by epsilon naught. But here we know the charges residing inside the sphere is 0. No charges are there inside the sphere, this shell. Nothing is there. So what will be the electric field inside this shell? It will be 0, because no charges are there to produce any electric field. So it will be 0, since charges inside the shell is 0. So this is the electric field intensity inside the shell. Now let's try to plot a graph showing the variation of electric field intensity of the shell with the distance small r. And you know small r is the distance of point P. Okay, point P from the center of the shell. So this total distance is small r. So what happens? The origin or the center of the shell can be considered as origin in this graph. And you know, inside the sphere or inside the shell, not sphere, inside the shell, electric field intensity is 0. Okay, so this is inside the cell, and let me consider one point here, and this point indicates small r equal to capital R. What do you mean by small r equal to capital R? Yes, this indicates the surface region of the sphere. Okay, so this point indicates the surface, and this region will be the region inside the sphere. Sorry, it's not sphere, it's shell. Again, I am making the same mistake, so please bear with the mistakes. Okay, so r equal to small r indicates the surface region, and the left side, that means this portion indicates the region inside the shell, and this region indicates, that means the right portion indicates the region outside the shell, because this is the surface. So when we move out of the surface, it will be outside the shell, and this region indicates the region inside the shell, the left side. And you know, inside the shell, what is the electric field? It is 0. Let me use another color to represent the graph. So inside the shell, electric field intensity is 0. So this portion indicates the inner region of the shell. Okay. Next, on the surface, what is the expression? On the surface, electric field intensity is constant. So let this be the electric field intensity on the surface. Okay. Next, and this is constant, and what is that? Sigma by epsilon naught. So this is the value of electric field intensity on the surface. Okay, this. Next, outside the sphere, what happens? Sigma r square by epsilon naught r square. That means here r square is in the denominator. So as the value of small r increases, the value of electric field intensity decreases, and that too rapidly. So outside the surface, the electric field intensity decreases with r. Hence the graph looks like this. It never becomes 0. You know, electric field intensity never becomes 0. It will only approaches to 0. So this is the graph. Okay. So this is the E versus R graph for a uniformly charged shell. So children, here we need to discuss another major concept related with the electric field intensity inside the shell. So you might have learned this thing, that means electric field intensity inside the shell is 0. Not only inside the shell, electric field intensity inside the conductor of any shape is 0. And this fact or this concept is electrostatic shielding. And due to this reason, we will say it is safer to sit inside the car than standing outside during lightning, because this car can be considered as equivalent to a shell, because no charges reside inside the car. So electric field inside the car will be 0, and during lightning, when we sit inside the car, there is no possibility to receive a severe electric shock, and thus we are safe. Okay children, so this is the concept of electrostatic shielding. So next we can discuss how this Coulomb's law can be derived from a Gauss's law. So for that, again we need to consider a point charge Q, and we need to consider a point P situated at a distance r from Q. Construct a Gaussian surface enclosing the point P, then only we can apply the Gauss's law. Now consider a small surface element here, and what is the direction of area vector? This will be the direction of area vector. Again, what will be the direction of electric field? Since it is a positive charge, electric field also acts radially outward. So the angle between electric field and area element will be 0. Okay, now we can apply Gauss's law. What is Gauss's law? Closed integral E dot dA is equal to Q by epsilon naught. Now when you expand this E dot dA, you will get integral E dA, because the angle is 0, so cos 0 is 1, equal to Q epsilon naught, right? Then electric field intensity is constant, so it can be taken outside the integral. Then you will get integral dA equal to Q by epsilon naught. Now therefore E equal to E into, what is integral dA? Integral dA is A, that means area of this whole sphere, and you know the surface area of the sphere is 4 pi r square, where r is the radius of the sphere, equal to Q by epsilon naught. Therefore the electric field intensity E equal to Q by 4 pi epsilon naught r square. And we can rewrite this expression like this, equal to 1 by 4 pi epsilon naught into Q by r square. Okay. Now, we need to find out Coulomb's law, or we need to derive Coulomb's law from this expression. So suppose I have placed a small charge, that means another charge delta Q here at the point P. Okay. Let another charge delta Q be placed at the point P. So what will happen? Here we have two charges, one is plus Q, another is delta Q. So obviously there will be a force of interaction between the charges. And how will you find out that force? What is the expression to find out the force acting on any charge? That is Q into E. You have already studied it. So here our charges, we need to find out the force acting on the delta Q charge. So our expression for force will become delta Q into E, right? And we have already got the expression for electric field intensity. What is this? 1 by 4 pi epsilon naught into Q by R square. So just substitute that expression here. So you will get force is equal to delta Q into, what is E? For E you need to substitute this expression here. 1 by 4 pi epsilon naught into Q by R square. And just rewrite this expression like this, equal to 1 by 4 pi epsilon naught Q into delta Q by R square. This is our Coulomb's law. We have studied Coulomb's law as 1 by 4 pi epsilon naught Q1 Q2 by R square. Q1 was one charge and Q2 represents another charge. So here instead of Q1 Q2 we have Q and delta Q. And this Q and delta Q represents two different charges. Okay children, so thus we have derived Coulomb's law from Gauss's law. So try to do the derivations along with me. If you have any doubt, pause the video, rewind the video and again go through the steps. Okay. So with this I am concluding. That's all for today's session. Notes of the topic and YouTube video has been uploaded. Just go through that. Also there will be a small test followed by the sessions. Attend the test and post me the answers quickly. We will meet in the next session. Till then, take care. Stay home, stay safe, keep learning. Thank you.